Hi everyone, my name is Zoë Webb Mack, and today I'm going to be talking about a background evaluation of the chiral vortical effect using a multi-phase transport model, also called AMPT. And just for a little bit of introduction, high energy heavy ion collisions produce quark-gluon plasma, also called the QGP, in which quarks are deconfined compared to their usual arrangement in which they're confined within hadrons by the strong force. And so special properties and behaviors emerge in this medium, which can only be produced under extremely high energies. These behaviors are of fundamental importance to the field, the study of quantum chromodynamics and QCD topology. And so one of these properties is the chiral vortical effect, also called CVE. So since the QGP created during a collision event has a chiral imbalance resulting from a vacuum transition, the plasma's net vorticity, here represented by omega, results in an observed baryon number separation across the reaction plane, also represented here by J. And so this baryon separation has been demonstrated in experimental data from the relativistic heavy ion collider STAR experiment. However, the contribution of background effects to this separation has not been accounted for. So here we're studying lambda proton interactions, which we choose in order to avoid contributions from charge-dependent effects, and apply a multi-phase transport model, AMPT, to estimate these background contributions. And so just for a quick summary of AMPT, AMPT is basically a widely used model that realistically simulates background conditions describing contributions from four phases. These are the initial conditions, partonic scattering, quark coalescence for hadronization, and hadronic scattering. And so basically these phases are considered to represent background effects. So here AMPT is used to simulate background data based on these phases for collisions between gold atoms at 200 GeV. And so, as I mentioned previously, in order to study the chiral vortical effect, we're interested in basically observing baryon separation. And so a Fourier expansion, shown here at the top, of the azimuthal distribution of particles gives us coefficient A1, which is related to the baryon number separation of particles. And so in order to measure this separation, we take a 3-point correlator called gamma, represented here, it's also called gamma 112, which contains terms that are dependent on A1. And so we can use this correlator to detect baryon number separation. And then delta gamma here is basically the difference in gamma values for opposite sign and same sign contributions. So basically, if delta gamma is non-zero, that represents a measure of baryonic separation. And then we also have another correlator, gamma 132, which is shown again just below gamma 112. And this basically provides a measure of background effects. Likewise, our kappa values here also provide a normalized measure of background data. So I'll talk really quickly about some of our results. So basically the figures here represent values with respect to centrality, which you can see here on the x-axis, which basically describes how peripheral a collision is. 0% being the most head-on, and with higher centralities representing more peripheral collisions. And so in the data generated by AMPT, V2 and delta delta, represented in the top two figures here, are both centrality dependent and positive. And so the coupling of these two values leads to background contributions in gamma. And so indeed, in this figure, you can see delta gamma, both 112 and 132 are positive, representing background contributions to gamma. And so AMPT data demonstrate non-zero delta gamma correlations between lambda and protons. So that is under the phases described by AMPT, which again, we take to mean background effects. Some baryonic separation is observed. Thus, the experimental observations of baryonic separation can't be entirely attributed to the chiral vortical effect and may, at least in part, result from these background effects, which are described by AMPT. Additionally, we find that the normalized value, kappa 132, is between 2 and 1. So this provides a good baseline of background signal from AMPT. Also, kappa 132 is a reasonable first order approximation of kappa 112, which we see in the figure here. And so these kappa values, which are normalized, may be used to compare simulated and experimental data in order to interpret experimental results. meaning that in future studies, kappa can be used to compare background data and experimental data to parse out the contributions to baryonic separation from both background and chiral vortical effects.